Thank you all for joining. My name is Arvind. I come from ETH Zurich, and today I'll be giving a presentation on our research, looking into the global role of community-scale multi-energy projects for net CO2 emission reductions. It's an energy system analysis, so it's a bit different from what we have been seeing today. So my problem really starts at home. As of today, 17% of global CO2 emissions are coming from residential energy end use. More specifically, 63% of our space heating needs is coming from fossil powered sources. In the cooling sector, while it is mainly electrified, the larger problem is the fact that in the coming future, we are expecting a significant rise in the cooling sector. So as of today, while 18% of the electricity demand is going into residential energy end use, this is expected to rise as cooling is getting electrified. We are electrifying our transport as well. So if the state of the art continues, the 17% global CO2 emissions are likely to go up. The good news here is that we already have solutions that are needed to mitigate this emission rise. And these solutions are closer to home. These include electrification of the heating sector and then decarbonizing the electricity sector through modular renewable technologies. And then we can penetrate more renewables with the help of storage systems. So the question I asked today is not really how do we decarbonize the residential energy end use emissions, but rather how much can we decarbonize them. So the focus of my project is really to analyze net emission reductions that come from these central solutions. These include community scale renewable projects, energy storage solutions, such as battery or thermal storage solutions and electrification. And I analyze all of this through this MES analytical framework, which consists of all the distributed generation and storage technologies that are comprising in that project. So why this analysis matters is because we have advantages and challenges that come with this energy transition. The advantages are that these are mature technologies which are much easier to deploy and they have much cleaner operations. In some cases, they are found to be affordable, and the resilience is one of the key aspects to these systems. I will not touch upon resilience today. But that is also something we have quantified in our work. And when it comes to challenges, it's important to understand that these systems are localized, which means that they depend on the local climate in which they are installed or deployed, and also on the grid characteristics. As we can see, the system depends highly on external factors such as the grid carbon, such as the electricity grid, the natural gas grid, and the demand profile. So the question of how much emissions can the system reduce is incomplete without asking also where are we talking about, and that is why we do this analysis on a global scale. The other two challenges are related to the number of technologies that we are adding near our end users. And this added complexity leads to more uncertainty because there are more technologies with the varied costs and economic parameters and performance parameters. And we may be, although we are introducing cleaner operations, we might be shifting our problems to somewhere else. That's why life cycle emissions are important to consider here. This brings me to my research questions, which are three. First is how much emissions we reduce. Second is where are we talking about, and at what costs. To answer this research question, I follow a typical uncertainty analysis framework. In the first step, we first need to characterize representative locations, because since the analysis is global and we can't do it for every point in the world, we need to identify some cluster locations. And for that, we make use of three publicly available data: the Köppen-Geiger climate map, which classifies the world around into about 20 climate zones, with each climate zone characterized by its annual temperature variability, precipitation, etc. And then we have the global solar and global wind atlas, where which actually at a very highly resolved level give an indication of the renewable potential of wind and solar. So once we have our representative locations, overall, I end up with around 174 representative locations globally for my analysis. And I can get the time series profiles for these locations through open data. Then once we have for each representative location, we do characterization of other non-climatic parameters. This would include like technology prices, the technology performance parameters, the grid parameters, the prices, etc. And then once we have characterized all our input, we sample one of the inputs and we apply it an optimization model and then we analyze our findings. A bit on the models. The model is a multi-objective mixed integer linear program where we try to optimize three objectives: cost, emissions, and expected energy not served. And so this leads to, since these three objectives are have nonlinear trade-offs with one another, they generate a Pareto frontier. But we want to focus only on the knee of the Pareto because this provides us the best compromise solution, and we get the knee of the Pareto through this normal boundary intersection method. Today, I'll focus only on emissions and a bit on cost, but not so much on the expected energy not served. Right, moving on to the results. So throughout the results, I'll be comparing two systems, the business as usual and the multi-energy system. So in the business as usual, we have gas-fired heating, electrified cooling, and in the multi-energy system, we have all the technologies that I mentioned. I cover end-use space heating and cooling demand, and the system is supplying around 30 gigawatt hour of energy to the end users, which, depending on the energy consumption per capita, can comprise of a household of few hundreds to few thousands. Right, so I'll start with the net emissions reduced. I divide my results among the 4 high-level climate zones, which are tropical, arid, temperate, and oceanic climates. Within each climate, I show the cumulative density of the change in emissions overall, which means that if it is negative, that means we are reducing emissions. If it's positive, we are increasing emissions. And the cumulative density gives us an indication of what is the likelihood that that we are reducing our emissions. So I divide the results into 9 classifications of low, medium, and high grid emissions, and low, medium, and high grid prices. And what we can see is the influence of grid carbon intensity differs among climates. We see the most between tropical and oceanic climate, where we see that a grid which has already low grid carbon intensity, introducing these systems has a very low likelihood of really reducing emissions because the life cycle emissions start to play a role. When it comes to high grid emissions, it does not really matter. In the oceanic climate, we actually see it does not, the grid carbon intensity does not influence our likelihood of reducing emissions at all, because here the major emissions are coming from the heating sector and not really the electricity sector. And since heating has to be decarbonized, so here the electricity grid carbon intensity is less relevant. So it gives us an indication it gives us a policy insight, especially for larger countries which are setting high-level emission targets. We need to recognize the regional differences in climates to set emission targets for at a central or federal level. This applies to countries like US, China, and India. In this world map, I show the medium change in emissions over business as usual. And I classify the results into 9 categories. And on the right side, we have the same change in emissions overall as a function of the percentage of global demand. What we see is that the most suitable, the regions where we achieve the least emissions are the ones in the northern parts of the world and parts in the southern hemisphere, which have high heating demand, and they range from 50 to 64%. More importantly, they cover about 75% of the global demand for space comfort needs. When we come to more warmer parts of the world, here the grid carbon intensity plays a role. So regions with high grid carbon intensity, these are regions like India, the Middle East, Indonesia, they would still benefit with in terms of through community projects by renewable penetration at community level. But parts of Sub-Saharan Africa and Brazil have very low grid carbon intensity. And so emission reduction through community scale renewable and electrification projects may not will need to consider the life cycle impacts of these technologies. So Of course, net emission reduction is not the only reason why you would want these technologies. The reason could be also resilience resilience and affordability. But impact of life cycle is especially relevant in these parts of the world. Overall, 90% of the cases we see of the global demand emissions are reduced. I show the same maps now for affordability, which is the change in costs over business as usual. Again, negative is good, positive is bad. Here we see that the influence of climate is much less relevant. But what is more relevant is actually the retail price of electricity at which you're buying. And here we see that high grid prices, which are more than 300 francs or dollars per megawatt hour, we are very likely to be affordable. But for less than $150 per megawatt hour, it is very less likely to be affordable. What we find is that most of the world actually pays less than $150 per megawatt hour, and actually these systems have very low affordability. It's only 12% of the global demand actually is right now affordable, considering the full range of uncertainty in our input parameters, and these regions are concentrated in Western Europe. Regions like Australia, New Zealand, and Canada are closer to being affordable, but the bigger, but more still affordability remains a challenge in most parts of the world. This brings me to my conclusions of my analysis. So firstly, we wanted to investigate how much emissions we reduce, and we find that for almost 3/4 of the global demand, we are able to reduce around 50 to 60% of emissions through community scale projects on renewable storage and electrification. Where do we do that? One key learning from this is that we see regional differences on the net emissions reduced through these projects, and it emphasizes the varying importance that decentralization will play in the energy transition with respect to net emission reduction. Affordability remains a challenge, and while we see that these systems are very good for emission reduction, we find that in most cases it is likely to be not affordable for people. So innovations in finance and improvements in technology are key to reach net zero. We find that we still are quite far away from it as in the state of the art. Thank you all for your attention, and I'm happy to take questions.
Thank you for the presentation. Are there any questions?
Hi, thanks for the brilliant presentation. Obviously, you mentioned, especially towards the end, affordability or you optimize the cost in general. I'm not sure if you mentioned it before, but do you include operational costs compared to capital investment needed at the beginning, especially since a worldwide study? Does it make a difference in cost if there's already a system in place or transitional costs, like reconstruction of the current system, or how's that? Is that included?
So operational costs are considered in the optimization. So it is also part of the cost objective. But this approach is a greenfield approach. So we do not really consider what other for each of the individual provinces or countries. We do not really consider what is already in place at the household or community level to this analysis. This is more like trying to look into the influence the climate and the surrounding grid has on the benefits that these projects can offer, and how do they vary across the grid.
Regarding affordability, so you mentioned limited places like West Europe. So can you share more insight on why those places is more affordable countries?
The most influential parameter in our input-output correlation is found to be the retail price that people pay, and Western Europe is the highest right now among all the regions. So And that's what makes it, that's what makes these systems much more affordable.
Any other questions? With no questions, let's thank the speaker. Thank you. So our next speaker